Okay, maybe it's working now. All right. I guess it didn't like the other mode that it was in. So unfortunately, I didn't bring my drawing tablet with me, so I have to kind of draw directly on my screen here. But I guess we'll just make the best of it. All right. So we left off kind of talking about some Bayesian ideas, and we had the beta distribution. Okay, and the way the PDF of the beta distribution is basically 1 over this beta function of a and b, and then we've got it's x to the a minus 1 and 1 minus x to the b minus 1. Okay. And we said this is good for simulating, or not even simulating, but kind of modeling PDFs where the output needs to be some kind of probability, okay? And so this might be what maybe a beta 5 comma 5 distribution looks like. The output of all of these beta distributions are going to be between 0 and 1, okay? And so let me actually just pull up just a tiny snippet of code to just kind of draw several of these beta distributions for us. Okay, so here I just have here. Let me make the text a little bit bigger for you guys. Okay, so we can say A and B are both 20, S, P, and then we can plot this. And here I just threw everything into a function called graph G beta for graph beta. And so here I can say, what if we graph beta with 5, 5, and it looks like this? What if I graph the beta distribution with 50? I guess we can do 20, 20, and then 50, 50, and then maybe 500, 500. Okay, and I think we saw this on Monday. So this is beta 5, 5, beta 20, 20, beta 50, 50, beta 500, 500. Okay, and the output is always between 0 and 1, but as we go higher and higher, it gets thinner and thinner. And we can think of this as kind of, if you saw, if we were drawing marbles out of the pouch and we drew 500, like we drew marbles at random and we saw 500 red and 500 blue, we can be pretty confident that the contents of the pouch is somewhere close to 50% red and 50% blue, okay? Whereas if we drew only 40 marbles total, where 20 are red and 20 are blue, we would also think that the most probable proportion is 50% red and 50% red, but we're a little bit less confident, and so we've got more spread here. Okay, and similarly, if I take any of these things and we kind of flip this around to say we've got 10 and 50, our proportion will look like this, where it's centered at 0.2, or actually maybe 10 and 40. 10 and 40 will be centered at 0.2 because that's saying we drew 50 marbles, 10 were red, 40 were not red, or 40 were blue. And so we're thinking, 10 out of 50, something around 20%. If I reduce this just down to 1 and 4, this is actually centered at 0.2 as well. If you take the mean of this whole thing, it looks a little bit messy, but that's what we have. 2 and 8 would give us kind of the same proportion. We get something, kind of very wide. And, we can kind of take it to the extreme and do 200, 800, and we get something centered, still centered at 0.2, but, a bit more reflective, that we're very confident that it's something around 20%. Okay? So where we left off was we were talking about baseball. And okay, so because I don't like writing on my screen directly here, I'm going to just pull up a Word document and start typing some stuff. We'll work it out here, okay? And the story was that in baseball, we have kind of a few key ideas here. Is that we're talking about baseball batting average, okay? We have almost everyone is above 0.2. Most are under 0.3, and anything higher than 0.4 is almost impossible. Okay, and so we can reflect this in a using the beta distribution. Okay, now I'm modeling. I'm going to kind of follow an example of a blog post that is that's online here. Okay, and so the author of this blog post also uses the baseball batting average example, and to model kind of his prior understanding or prior knowledge of the batting average kind of distributions, he decided to use a beta distribution with shape parameters 81 and 219. Okay, so let me see if I can go there. I'm having all sorts of technical issues. Okay. Okay, so one possible choice is beta with A equal to 81 and B equal to 219. Okay, and if you look at this, 81 and 219 add up to 300, and 81 divided by 300 is around 27%. And so this is, you know, in my opinion, a little bit optimistic about batting averages, but let me go ahead and I will just kind of plot what beta distribution with shape parameters 81 and 219 look like. Okay, so if I graph this, this is what the distribution looks like. Let's go ahead and just kind of blow this up. And what we see here, what's the quick way to add tick marks to, do I just do axes at equals sequence 0, 1 by equals 0.1? Yeah, I don't know. Okay, but it doesn't matter. Okay, but what we'll see here is that this is actually centered at 0.27. Okay, this peak occurs at 0.27, and we see that it dramatically drops off that where we don't have any kind of, it's, you know, you have very few people below 0.2. Okay, and then this upper end is probably like 0.36 or something, and you have very few people above 0.3 something. Okay, and with no one at 0.4. Okay, and so you know, this is one person's expression of their prior understanding of kind of the distribution of batting averages, okay, before we look at anything about an individual players. Now, someone else could say, you know what, I don't like these numbers. I don't like 81 and 219. I'd rather see something like 75 and 225, okay? And that would just kind of shift everything down a little bit, okay? And that would just be someone else's kind of interpretation of kind of this batting average distribution, okay? But we'll go ahead and we'll start with the beta distribution with shape parameters 81 and 219, okay? One possible choice, beta, with A equals 81 and B equals 219. Okay, and the example that I used was, you know, a new player, like a rookie, shows up, and we've seen the player go to have 10 at-bats, and he got hits 5 out of the 10 times. Okay, a new player has 5 hits in 10 at-bats. Okay, so this is, you know, the current batting average is 0.5, okay, or 500. All right, and maximum likelihood estimation says that the value of p hat, or I'm sorry, the value of p that will maximize the likelihood of this data is 0.5, okay? All right, but our intuition tells us that it is unreasonable to expect this player to finish the season with a batting average of 500, okay? Okay, so this is, I think, where we left off on Monday, right? And we said, okay, well, let's talk about the prior distribution and things like that. And so what we want to do is we want to be able to combine our current understanding of batting averages, which right now is modeled with the beta distribution of 81, 219, and somehow combine that with this data that we've seen where the player got 5 hits out of 10 at-bats, okay? Now, how can we go about doing this? All right, so this is where we are going to use Bayes' rule, okay? And so, so Bayes' rule says that, I'm just going to use the terminology. We have the posterior distribution is equal to the likelihood times the prior divided by the marginal. Let's go ahead and write it like that. All right, is that okay? We might write it this way. Probability of B, I don't know, how do we, what's the normal way we do this? We do probability of A given B times the probability of B given A times the probability of A divided by the probability of B. All right, so this is what we have, okay? And so here we're going to combine these using the likelihood of our data multiplied by the prior and the marginal here. Okay, so let's come back and I will kind of draw this out. Okay, so our prior distribution okay, so our prior distribution right now is beta 81, 219, okay, which is going to be equal to some beta function, and then I've got x to the 81 minus 1 times 1 minus x to the 219 minus 1. Okay, the data that I have seen is basically going to be a sequence of outcomes. And so, you know, maybe it's going to be hit, and then hit, out, hit, out. I don't know. I'm just making stuff up here, okay? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so we have, I'm just making this up, but 10 at-bats and 5 are hits, okay? Okay, And so we'll say let x be the probability of a hit, okay? Because that's what we have up here. In the prior distribution, x represents kind of the probability. Now, if you'd rather change everything so that we're not using x, we can change this to be p if we want to, and we would just modify our prior distribution to say p over here. Okay, that's also allowed. I don't know. Whatever you want to do. Okay. Do you guys not care? I think because I started with x, we'll go ahead and just stick with that. All right. So so keep in mind here the x up here represents kind of the probability of success. Is the kind of the probability of success, right? Because what we draw from the beta distribution is a value between 0 and 1, which we are using to represent kind of the batting average or the probability of getting a hit. Okay, and so now when we see our sequence of outcomes, it feels a little bit weird, but here we're going to treat x as the probability of hit, and I don't know what we're going to call the actual sequence here, but now what is the likelihood of our data? The likelihood of our data is going to be what? Okay, so how many hits did I get? 5, okay? So what is the probability of getting 5 hits in a row? Maybe just using the x is throwing you off. But if it was p, you would just do p to the 5, okay? But now x represents the probability, so it's going to be x to the 5. Is that okay? All right, and then so we have 5 hits, and then what's the probability of an out or not getting a hit? Okay, yeah, 1 minus x. And how many times did that happen? 5. Is that okay? All right, and so if I want the numerator of Bayes' rule, okay, the numerator of Bayes' rule, that's going to be the likelihood times the prior. And it's not a coincidence that it works nicely, okay? So the likelihood here is x to the 5th times 1 minus x to the 5th, okay? And the prior is just some constant times, maybe I shouldn't use an x for the times there, times x to the 81 minus 1, and 1 minus x to the 219 minus 1. Is that all right? Okay, and so if I combine all of that, my numerator, so the Bayes' rule numerator ends up being, okay, so I have x to the 5th and 1 minus x to the 5th and a constant times x to the 81 minus 1, 1 minus x to the 219 minus 1. Okay, and so this is going to become x to the 86, or I'm going to just write this out. 5 plus 81 minus 1, okay, and 1 minus x to the 5 plus 219 minus 1, okay? And so, I mean, we could crunch this out and we would get x to the 84, but I'm actually going to leave it as 86 minus 1. And over here, I'm going to leave it as 1 minus x to the 214 minus 1. And there's a reason for that, okay? And I'm also going to just kind of roll up, and I'm going to just kind of ignore this constant and just change this to is proportional to. Yeah, question?
Is it 224?
Did I mess something up? Yeah, 224, yes, thank you. I cannot add. Okay. So I have 86 minus 1 and 224 minus 1. All right, is this all right? Okay. In Bayes' rule, okay, you have the probability of A given B is equal to the probability of B given A times the probability of A divided by the probability of B. Okay, this marginal probability, it is just a constant, okay? It's a constant. And the reason why we need a constant is so that the whole probability function will integrate to 1. Okay, that's really just the purpose of this constant. This constant serves the only purpose of just ensuring that our probability function integrates to 1. Okay, so I can graph this. If I graph this, I'm going to get something, you know, that looks like this. Okay, somewhere between 0 and 1. Okay, and the problem right now is that this will not integrate to 1. Okay, so here I need to figure out some constant. What is the constant that we can use so that this numerator portion, after I multiply it by the constant, we need to either scale it up or scale it down, okay, so that the whole thing integrates to 1. Okay. Any ideas, any solutions in mind? Does this look like a probability distribution? It looks kind of like, huh? It looks like the beta itself, okay? And so, again, the beta distribution already includes the constant that gives us our answer, okay? So, so here we have this, and the beta distribution, the numerator, this part, the numerator in the beta distribution looks exactly like this, okay? And it's just, we have a constant, all right? And the reason why I left the minus 1s is because in the beta distribution we kind of have a minus 1. So this is basically, whatever this is proportional to a beta distribution with shape parameters 86 and 224. Okay. Okay. And kind of the logic here is that because we know the result of Bayes' rule has to be a probability distribution that integrates to 1, and we know that this thing is proportional to the beta distribution with shape parameters 86 and 224, that's the only, then this thing is going to be the beta distribution 86, 224, because that's going to be the only probability distribution that's proportional to this, okay? So the result is that after 5 hits in 10 at-bats, the result is that our kind of the distribution for the batting average is going to follow a beta distribution with shape parameters 86 and 224. All right, so let me just kind of write some of this down, okay? So our likelihood, so if we say x will be the kind of the unknown batting average of the player, okay? So this is a random variable, okay? The likelihood of observing a sequence like hit, hit, out, 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 hit, out, I don't know, hit, out, hit, or something like this, is going to be x to the 5, 1 minus x to the 5 as well. All right. The prior is equal to constant times x to the 81 minus 1 times 1 minus x to the 219 minus 1, okay? And then the likelihood times the prior ends up being x to the 6 minus 1 times 1 minus x to the 24 minus 1. Okay, and basically the only probability distribution be proportional to that is the beta distribution with shape parameters 86 to 24. So I just kind of want to pause here and make sure we're okay with jumping to this. Okay, and so here's the thing. We can graph this. We can see, all right, well, what does the beta distribution with 86, 224 look like? Okay. So let me so we got here's 81, 219, okay, and here is 86, 224. All right, it's ever so hard. If you look, it just shifts it up just a tiny bit. Okay, so before we saw the player play at all, we said, okay, kind of the most, according to this, the peak is at around 27, batting average of around 270.27. Okay, and after observing 10 at-bats with 5 hits, we're going to, we just shift up the prior probabilities just a tiny bit, okay? We just kind of advance it a little bit. Maybe I can just kind of plot this directly. So I'm going to do sequence 0 to 1 y equals 0.01. We're going to do S d beta S versus 81, 219. And then I'm going to do lines S86, 224, and I'll just shift the color. Color equals red. Oops. Oh, call is red. Okay, and so this is what we see. Okay, after 10 at-bats and a few more hits, okay, before we knew anything about the player, we said kind of the most probable batting average is around 0.27. After seeing 10 at-bats and 5 hits, we adjust that ever so slightly and we say, okay, at the end of the season, kind of the most probable batting average may be like 0.28 or something like that, okay? 0.29 or something. We just shift it over a tiny bit, all right? And I think that makes a little bit more sense to us if we understand, like, with our kind of prior knowledge of baseball, knowing that it's almost impossible for someone to finish a season with a batting average, higher than 0.4. Okay. We're not going to just take our maximum likelihood estimate, which says, in 10 at-bats, we saw 5 hits, therefore our maximum likelihood estimate is 0.5, okay? We're just going to say a batting average of 0.5. That's just ridiculous. That doesn't make sense in this sport. And therefore, we're going to just kind of shift things up just a tiny bit, okay? Now, we can also see how this is subject to different people's starting opinions, okay? So here we had kind of the prior probability was modeled with the shape parameters 81 to 19, okay? Someone else may start with a prior distribution of beta, not 81 to 19, but maybe beta 75 to 25 or something like that, okay? And, okay, so tell me if we have, again, kind of the same situation. We have 5 hits, 5 outs, or a total of 10 at-bats. What will the posterior distribution be? Okay, so, all right, did anyone figure this out? So again, we would follow kind of the exact same work here, except all we're changing is this from 81 is going to be changed down to 75, and 219 will be changed to 225. Okay, and then if you look at what's happening, the likelihood is going to be the same, where it's going to be x to the 5 and 1 minus x to the 5. And when we combine those, we're adding 5 to those shape parameters, okay? Okay, so what will the posterior distribution be? So this will be an exercise, I don't know, on your own. Exactly, so we're gonna have beta with shape parameters 80 and 230, okay? Is that all right? You guys can try that out. Okay, all right, so what does that look like? So here, let me delete this, all right? So here we've got this, this, and this. Okay, so this is one where we had one prior distribution, and let me just show you the other one. Okay, so we're gonna start off with 75, 225, and now I'm gonna go to 80 and 230, okay? So this is a new plot, and this. Okay, so the difference is one person, we started off with kind of the batting average is the most likely is around 0.27, and over on this side, the most likely batting average is around 0.25, okay? And basically the pictures look almost the same. The black line is the prior distribution, and then the red line is our updated distribution after seeing the player play with 10 at-bats, okay? And with 10 at-bats, we just shift our thing just a tiny bit, okay? And so our overall batting average just shifts up, to have a peak of around 0.28 or something like that, okay? What would happen if we had observed even more data? Okay, so let's say we're gonna go back to our prior is beta 81, 219, okay? And then we observe lots of data. or I don't know, more data. Okay, and let's say this player is doing phenomenal, right? We have, now we've observed 100 at-bats, okay? And we have something like 42 hits, okay? So we have 42 hits out of 100 at-bats, okay? So, it's not as high as 5, it's not 5 out of 10, so it's not 0.5, but 42 out of 100 is really, really, really good for a baseball player, okay? And so how would we combine this? Now that we've seen more data, we can probably be a little bit more confident in the kind of that the batting average is, you know, going to be quite high, okay? And so so again, if you kind of follow the math for this, if we have so again, the prior is a beta with 81, 219, and that's going to be you know, constant x to the 81 minus 1, 1 minus x to the 219 minus 1, and then the likelihood is we have, you know, 42 hits and basically 58 miss. So that's going to be x to the 42, 1 minus x to the 58. And when we do the likelihood times the prior, we're going to get something proportional to x of 42 plus 81 minus 1, and 1 minus x to the 58 plus 219 minus 1, okay? So all we're really doing is we're just adding the number of hits to kind of the first shape parameter and the number of misses to the second shape parameter, okay? And so this ends up being proportional to the beta distribution. So x plus 80, what is that, 123 minus 1. This is 1 minus x to the 200, I can't add, 77 minus 1, is that right? Did I add that right? Okay. Okay, so now we're going to have beta with shape parameters 123 and 277. Is that okay? And we can graph that. So the prior is 81, 219, and then the result after we combine everything is going to have 123 and 277. And I think so. Let me. Okay, so the prior distribution has a peak at 0.27, and after observing a lot more hits, we have shifted up our kind of you know, what we think the player's performance to be a lot higher. This is centered probably around I don't know, 123 divided by 4, around, you know, 0.31. Okay. This is where we're centered. It's a little bit higher. You know, still not as drastic as going up to 0.42 or something like that. Okay, so we are taking into account, you know, the fact that we have more data shifts the resulting distribution more, right? So earlier, when we only had 10 at-bats, the amount that we shifted. Let me just delete this one. Okay. Okay, so this is what we had our prior distribution is this, and we saw 10 at-bats, and the player had very good performance, 5 hits out of 10 at-bats, and we said that's good, and so maybe we're going to have a good player, but because it was only 10 at-bats, the amount we shifted was just a little bit, okay? Now we've seen 100 at-bats, okay? And so the prior distribution is still centered at 0.27, but now that we have seen more data, more at-bats, the amount we've shifted is even more, okay? And so this is just kind of a reflection of how we can combine what we see in basically this Bernoulli situation where, you know, the player either gets a hit or a miss, and, you know, the amount of data that we've seen, combine that with the original data. And then, you know, if you see even more data, okay, and this is a little bit silly, but let's say, you know, so if we start off with 81,219, and let's say we see 1,000 at-bats and there are 400 hits, okay? So if I just do 400 and then I add 600 to the other side, so we're just taking, with 400 hits out of 1,000 at-bats, okay, we're going to add 400 to the shape parameter, first shape parameter, and go from 81 to 481. And then we're going to add, 600 to the other shape parameter, going from 219 to 819, okay? And if I graph this, you can see this was our prior distribution centered at 0.27, and after seeing 1,000 at-bats with 400 hits, you know, we're centered almost very closely to 0.4, okay? We're a lot higher, and we're a lot more confident in the result. Of course, it would be incredible to see any player achieve 400 hits out of 1,000 at-bats or something like that, but this would be kind of the result that we would get there, okay? All right, we'll stop there, and we'll see you guys on Friday.